As you know, Angus, our little subject does not seem to understand the gravity of the situation.
How do you figure, sir?
Well, we told him that if he didn't listen, then bad things were going to happen.
I understand that, but what has he done wrong?
We told him constantly that if he didn't stay away from company affairs, he would be hurt.
Yes, we did, sir.
I have built this company from the ground up. This company is finally starting to make money just like I imagined, but it could all be ruined if he continues with his plans.
So, what do you want to do?
Eliminate the problem.
So, murder?
Good God, Billy, no! That's messed up! Seriously, I was just thinking that if we just show him the danger of his plan, then he would stop his actions.
Alright, so what did you have in mind?
3 very specific events should be enough. First, let's interrupt his morning jog. He loves to jog every morning. Now we know this from our covert operations unit. So, we're just gonna let him almost get hit by a car. You know, see what can happen.
But sir, that's madness. Surely he'll be hit.
Ye of little faith.
And how can you be so sure?
Kinematics, my dear friend.
Explain.
So, Angus, as you see from this diagram, our subject will be on his morning jog. Now, we'll just drive our car at a relatively safe distance. Now, what he doesn't realize is that when we'll come up on the oncoming direction as he's jogging, and as you can see, we're going to give him a little wake-up call. So, our car will be traveling at the constant velocity of 25 meters per second. Oh, by the way, let's assume this is an ideal world, in which case there is no friction. So, just getting that out there. So, we're going to be traveling at the constant rate of 25 meters per second. We're going to come to rest in a span of 3 seconds. In which case, we need to figure out how much space we need to leave between us and our subject so we can hit the brakes and come to rest just before we hit our subject square. So, as you can tell, we have this equation, x equal 1/2 times the sum of the velocities times the time. We have 1/2 times our constant velocity, which is 25 plus 0, so 25, times our time, which is 3. 1/2 times 75 is 37.5 meters, in which case we need to start braking just at about 37.5 meters away from our subject, in which case we will not hit him. It'll be close enough that we can scare him, but we won't hit him. So that'll be our first encounter with our subject, as to give him a near brush with death.
Brilliant. That'll keep him away.
Oh, but we've only just begun. Now we move on to the second part of this operation. You know, free-falling fear. The 3 F's, if you will.
We can't expect to drop something and assume it won't hit him. Isn't the whole point just to scare him away?
Shut up, Angus! You just have to learn to trust the laws of physics, and everything can be solved.
The almighty science.
Go on.
Well, this one has 2 parts. Primarily, we know where he retrieves his mail every day at 4:15 p.m. That's when we strike.
What do you mean by it? How do you keep doing that?
So, Angus, as you see I'm over here now, so our subject will be walking at a constant velocity of 1.5 meters per second to his mailbox where he will retrieve his mail. Now, we have done some intense studies, and we will set up a perch about 10 meters above his mailbox. And we'll drop an object, as seen in this figure, we'll drop an object from that 10-meter point. It'll fall off the ledge and come to rest right in front of him. Now we just need to figure out how much time the ball will take to fall so we can figure out exactly how far it's going to travel and thus it doesn't hit him. So we've done some very intense calculations here. We know that our point, like I said, is 10 meters above the ground. As we know, the ball's initial velocity in the y direction will be 0 meters per second, so we can ignore that. The ball's acceleration in free fall is negative 9.8 meters per second, as we're calling down negative. We're calling the negative direction in the downward direction. So, also, we know that our variables in the y direction have been solved for, so now we can just proceed to the calculations. So we have our equation y equals v naught t plus 1/2 at squared. Negative 10, because it's negative down direction. Negative 10 equals 1/2 times our acceleration, which is negative 9.8, times our time squared. So we're going to solve for our time, which we can then plug into our x equation and figure out the distance that the ball will travel in the x direction. So as you see here, we have negative 10 equals 1/2 times negative 9.8 t squared. 10 divided by 4.9, so we cancel out the negatives because we're positive thinkers. So
Obviously.
10 divided by 4.9 equals our t squared. Our time squared comes out to 2.041. Take the square root of that, we get t equals 1.429 seconds. Bring that over here to our x direction, where we have our initial velocity equals our final velocity, because in the x direction, the velocity is constant throughout free fall, so we don't need to worry about changing velocity. So v naught equals v, velocity equals 5 meters per second. Our acceleration is 0 because, like I said, constant velocity. Time equals 1.429 seconds, which is what we found over here, and our x is what we're trying to solve for. So, as you can conveniently see on this right half of the piece of paper, we have velocity equals our distance traveled over the time. We have, when you multiply through by time, you have the velocity times your time equals your x displacement. So you have our velocity, the ball will be falling at a velocity of 5 meters per second in the x direction. So 5 meters per second times our time, which is 1.429, equals our x displacement, which comes out to 7.145 meters. So that being said, the ball will travel 7.145 meters from its release point at the ledge. So we will make sure that when we drop it, it will travel that required distance so that the ball does not hit our intended subject.
That's fantastic. What's our final move?
This is the master of all, the mother of all physics projects, the granddaddy of them all.
Go on.
See, the subject is really self-conscious about his weight.
I heard that.
So what we need to do is make him believe that bad things are really and truly happening. See, he rides the elevator every day to work. But what we really need to do is make him believe that he's gained a lot of weight over Thanksgiving. As he's in the elevator, we know that his weight will increase as he takes the elevator up, because he'll see the scale, step on it, and think, oh, let me weigh myself. But truth of the matter, he's gained a lot of weight over Thanksgiving. Oh God, I'm so fat.
But won't he know what's going on?
Nah. Poor Sab never took physics class. Zoology major.
When does this go down, sir?
0100. Operation Diamondback Splash officially begins.